Hey, hi everybody. Welcome to the LinkedIn's stream processing meetup this evening. My name is Gary, along with FA and DJ. We'll be hosting tonight's meetup. I'll spend a minute to do a quick introduction about the meetup, and then we'll be on our way on 3 exciting talks. Okay, so this is the agenda for today. After this introduction, we will have a talk about trust but verify, a deep dive into correctness of Apache Kafka replication protocol, followed by declarative reasoning with timelines. And also lastly is the decoupling compute and storage for stream processing systems by our 3 speakers. A reminder, the talk will be recorded and we will be uploading the video to YouTube LinkedIn channel. So you can always go back there for more information. One thing I would like to sort of call out is during this time, we'll be sort of interacting with the speakers through the Q&A function in Zoom. So you'll see that little button over there. So you can submit your questions at any time. At the end of the talk, we will be selecting the questions and present it to the presenters. And then I think after that, presenters can still answer the questions offline during the seminar. All right, so finally, if you are interested to also participate in the meetup and share your great ideas in stream processing, so feel free to reach out to Adam, FA, David, and myself. Okay, with that, I will pass it on to FA to introduce our first speaker. I'll stop the sharing now.
Thanks, Gary. So our first speaker is David from AWS. And David has a decade of experience in building large-scale data storage, movement, and retrieval systems at Amazon. He has bootstrapped multiple products and teams across different geographies, with Amazon Neptune, which is a graph database, being the milestone 0 to 1 story of his career. His latest adventure takes him into the data streaming world with an objective to enhance Apache Kafka. And today there's a very interesting talk that David will present. It is Trust but Verify, a deep dive into the correctness of Apache Kafka's replication protocol. With that, without further ado, I will leave it to David.
Thank you, Efe. All right, folks. Efe already talked a bit about me, so I'll keep it brief. But right now, my roles are to act as a committer in Apache Kafka. I recently got this privilege almost a month ago. And in my day job, I work as a senior software engineer at AWS. And since most of the audience are here in this particular streaming meetup is from Bay Area, so I thought I'll talk your lingo. I'm a 3X founder. Not really a founder, but I was a founding engineer for 3 different teams and products inside Amazon. And one of the key products was Amazon Neptune. I spent around 7 years building databases, specifically graph databases on the Amazon Neptune journey, starting from the query planning, execution, and at the end of the day realized, no matter whether it's databases or it's streaming, the distributed systems behind the scenes remain same. I started my open source journey over there, and I started contributing to a project called Apache Tinkerpop, and I currently am a PMC member over that particular project. So when I moved to distributed streaming from the databases world, one of my main objectives was to improve Kafka as well as contribute to open source. So in my current role today, these days, I wear 2 hats, the Apache Kafka hat, which is my open source hat, and then the Amazon hat for the Amazon MSK managed streaming Kafka. But I'm lucky from a perspective that both of these roles have an overlap for me, where both of these roles require me to ensure the sustainability of the community, that the Apache Kafka software is continuously growing, innovating for Apache Kafka. It's a win-win. The more Kafka grows, the better it is for the users of MSK. So with that, let's talk about what we're going to talk today. We'll start with the brief introduction to Kafka's architecture, since I don't expect a lot of familiarity with Kafka specific things from you folks, we'll just touch upon the concepts or set up some premise on what is a control plane, data plane from a Kafka's perspective, and where does the replication come into the picture. We'll also talk a bit about examples on how Kafka does fault tolerance and how does it ensure data consistency. In the second half of the presentation, we'll take the concepts that we learned about Kafka architecture, specifically about how replication ensures fault tolerance and data consistency, and then use model those particular concepts using a modeling language or formal specification language called TLA+. Specifically in TLA+, we'll take a couple of examples of Kafka being modeled on TLA+, and we'll see why or how that is useful in the day-to-day scenarios. And lastly, I'll briefly touch upon the future improvements that we could potentially do in Apache Kafka community using these particular tools. All right, so let's get started. Apache Kafka consists primarily of three different components. Here on the left side, you'll see that there's a producer. Producers are the clients which produce messages, which send messages. On the other end are the consumers. Consumers are the clients which receive messages. And in the middle, you'll see that the Kafka ecosystem or the Kafka server layer comprises of different machines or different servers. So Kafka acts as a distributed system, so to ensure scalability for the data consumption and production. So since it's a distributed setup, it's set up as a logical cluster. Each cluster consists of smaller number of nodes. Each node, the terminology that we use to have for these nodes are brokers. So Kafka cluster consists of multiple brokers, and a broker might play different roles in the cluster. There is one node in the cluster which acts as a controller. There is one node in the cluster which acts as a group coordinator. A group coordinator, and what is a controller and what is a group coordinator, we'll probably talk about it in a bit. And then there are multiple nodes in the cluster who might act as individual leaders for different partitions. So we'll also touch upon that. But the takeaway from our here is that distributed systems, there are brokers, and each broker plays a different role, one or many roles. So let's dive into that. The data storage at a logical level in Kafka is done in something called topic. What is a topic? Think of topic as a logical encapsulation of data. So in this particular case, a topic could be, hey, my website clickstream events or something of that sort. So a topic is a cluster level entity. Each topic has a unique ID, a unique name, and it's unique across the cluster. But then the data can be so large associated with one particular topic. We need a smaller granularity than a topic. Hence, a topic gets divided into smaller granularity, which we call partitions. What do partitions do? A partition helps you. A partition is a node level entity. So when we are saying a topic exists across the cluster, a partition exists on a broker. It is the actual physical layout or how data is actually stored. And it is also a unit or an entity that could be used for parallelizing. So if you have large amount of data, you distribute that data across different partitions. And each partition reside on one particular broker. One important point to note over here is the ordering guarantees provided by Kafka are at a partition level and not at a topic level. So if we are saying that, hey, from a consumption perspective, I want to consume all my events in an order, they would be consumed, they would be ordered for a particular partition, not across the topic. Inside a partition, we have messages, and each message is identified using an offset. The offset is starts from 0, and it's a monotonically increasing number, which uniquely identifies that particular message. We'll talk another bit about unique identification over here, because for the same partition in a distributed setup, it might occur that you might have, the same message, which is with the offset 0, being produced by 2 different leaders. And to disambiguate between that, we use something called a leader epoch, and we'll talk about that later in the presentation. But let's take a step back and see how the producer scenario looks like. So the producer or the client asks any random broker. It reaches out to the cluster, asks any random broker, hey broker, I want to send a message to partition A. Whom should I send the message to? That any random broker replies back to the client or the producer and tells it, hey, you should write the message to broker C, because broker C is the leader for your partition. What that means is that writes are always directed to a leader, and you can't randomly produce writes to any of the other brokers. So you need to identify who's the leader of a partition. So broker C, so a random broker tells back producer that, hey, you should send this message to broker C, because broker C is the leader for this partition. You send the message to broker C does some stuff, let's say some stuff for now, because we'll go into detail about that. And then it goes back to the client or producer and say, yay, your record is committed over here. Between step 3 and 4 over here, when we said that we send the message to broker C, what broker C does is it persists the record internally, and what persist specifically means that it writes it to its disk so far. But in another 6 months, when Kafka releases version 3.6, there's a new functionality called tiered storage, more commonly identified as KEP 405 in the Apache Kafka community coming up, where it would also allow you to store that particular message on a remote storage, such as you could store it on S3 or HDFS, which is shared across the cluster. So now there are 2 different things happening over here in this particular interaction. The first part, the question which the client or producer wants to know, who is the leader for a particular partition? That kind of information is what we call as the cluster metadata. And then there's this second thing which is happening over here, which is the writing to the leader. That is the part which we call the data replication layer. So we need 2 different consensus systems over here. The first to answer the question, first question, and second to answer the second question, or rather the question about where should I write to the leader or who the leader is. We'll talk about those 2 systems, one called control plane, the data plane. But before that, let's also look at it from a consumer perspective. From a consumer, the consumer is the client which is reading the information. It goes to a broker, it says, hey, I want to read message from partition A. Whom should I reach out to get that particular message? It can ask any random broker. And then the random broker goes back and says, hey, broker number A and broker number C are the in-sync replica or the ISR for partition A, which means that they have consistent data. You can read this data from any one of them. Then the consumer can choose any of one of these brokers, get the data from over there. Now, one quick note over here is this thing is sort of hackable in Apache Kafka, where it allows you to strictly say, no matter which are the partitions or which are the brokers in my ISR, I always want to read from broker A. And that's configurable. It's not on by default, but one use case where people use it is to prevent cross AZ or prevent cross data center network calls, which are more expensive. So they always want to read from the broker which is nearest to them. So we talked about two systems which we require. So the first system, the control plane system over here, is the one which would maintain the metadata, which would answer the first question when you ask a random broker, hey, which node should I read out to write data? Who's the leader for partition A? That's the control plane's responsibility. And then there's a data plane. Then these both are at a cluster level concept. Data plane's responsibility is to actually replicate the data and make sure that the data remains consistent. Let's talk a bit more about these two. So control plane is nothing but a consensus service where a group of different brokers agree to share a consistent view of the data. In this particular case, the data that they consistently see is the metadata of a cluster. And what is the metadata of a cluster? As the example we just saw, a metadata is the leader of who's the leader of partition A. That's stored in metadata. Where can I read messages of partition A? The consumer case, that's metadata. Or what is the configuration set for topic XYZ from an administration perspective? That's metadata. So we need a consensus service who can be fault tolerant so that if somebody goes down, you can still have access to that information. So that service is either, so what Kafka does is for that service, it can either use Zookeeper, which is basically, Kafka offloads this consensus responsibility to, hey, Zookeeper, you take care of maintaining this metadata. Or you could use Craft. Craft is the new mechanism, or rather the inbuilt consensus service for Kafka. Right now, for the purpose of this talk, we'll treat control plane as a black box. So let's just assume that there is a control plane which is fault tolerant and which gives you that particular data. Now, what does data plane do? Data plane is the concept where at a per partition level. So every partition has a leader and it has a bunch of followers. And this distributed setup is meant to ensure consistency of data in a distributed environment. So when you send data, which is the produce call, or you consume data, data plane is the component which handles this produce consume. A partition has n replicas. So a partition, you can define the replication factor for it. Amongst those n replicas, one would be the leader, and the rest of the n-1 would be called the followers. There's another concept of high watermark. High watermark is a checkpoint before which all the messages are considered as committed, which means that if a machine goes down, you can still read those particular messages. Then there's a concept of something called n-sync replicas. N-sync replicas are a subset of the n replicas that we talked about earlier, and they have a consistent view of the data. Since it's a set of machines, those are the machines where the consumers read from. Then we have the next concept of a leader epoch. Now, why would you need a leader epoch? So we talked about offsets, right? Offsets start from 0 and they are monotonically increasing. But let's say there are two machines who think that they both think that they are the leader. It is possible because of scenarios such as network partition that both those machines get an offset for that partition, let's say for offset 2, different messages. So for offset 2, first machine writes message ABC and the other machine writes message XYZ. Now, when we want to do reconciliation later on, which is to determine, do I treat ABC as a correct offset 2 message, or do I treat XYZ as the correct offset 2 message? That decision is based on this additional metadata that we store with each of the message, which is leader epoch. And what leader epoch means is it's a version, it's also a monotonically increasing version of the leaders at any given point of time for a partition. So when the leader changes, this version is incremented, and whichever leader wrote a particular message to the log, so that message contains the leader epoch. So in this case, we would have For the ABC, we'll have, let's say, epoch 2. For XYZ, we'll have epoch 3. And when we are doing reconciliation, we'll see, oh, epoch 3 is greater than 2, so it's more recent. So that's the one which we have to treat as the source of truth. Important point over here, I did talk about that clients only read from the in-sync replica set. But another point to note is clients can only read until the high watermark, because as the replication system goes through, high watermark is the criteria or the commit checkpoint, which tells you that all these messages before this point are already committed. Another interesting point to note over here is, or we'll probably talk about that in the next slide. But fault tolerance. So how does Kafka achieve a fault tolerance over here? Let's say we have this control plane, which we are treating as a black box for now, and it's talking to the data plane. Now over here, each leader in the data plane is heartbeating to the control plane, of making sure that control plane knows it's alive. In Zookeeper case, it has a watch with Zookeeper. So if the leader doesn't ping that watch for some time, Zookeeper knows leader is down and then initiates a leadership failover. So as you talked about, one of the primary responsibility of control plane is also to do leadership election. And so it detects that a leadership has gone down, does a leader election, and chooses the new leader. So in this scenario, leader goes down, control plane gets to know about it via a heartbeat. It tells follower 1 and as well as follower 2. So it sends a broadcast message to all the other replicas for that particular partition to tell them about the current state of the system at that point of time for that partition. So it tells everybody the new leader is follower 1, and a follower 2, you should start following follower 1 and start considering that machine as a new leader. So on getting that message, follower 1 will stop replicating data from the leader. Instead, it would start acting as a leader, which means it would start accepting writes. Because remember, we talked about that writes are only sent to the leader. So it would start accepting writes at that particular stage. And follower 2 will start replicating from follower 1. An interesting point to note over here is you might see other systems where a raft-based consensus is used or a quorum-based consensus is used. Over here in Kafka, like, it's very cleanly decoupled, that there is this external entity called control plane. It has its own consensus system. It could be raft-based, it could be Zookeeper-based, it could be something else. But there's this external entity which is always available, and that's the entity which does leader election for you. So another interesting point here is, now since we are saying inside Kafka, you have this control plane layer and then you have this data plane layer, which are two different entities. Can we scale them independently? Because you don't require a lot of machines for control plane since it hosts metadata, but you do require a lot of machines for the data plane. So yes, you can scale the control plane independently from the data plane, and the way how you do that is the brokers, which are part of the control plane called controllers, they can reside as a separate cluster altogether. So you can potentially have separate 3 powerful machines or 4 powerful machines acting as your control plane, and then have data planes spread across a bunch of brokers. Another interesting point to note over here with respect to the heartbeat is that heartbeat is one of the mechanisms to handle network partitions over here. As you're familiar, or you can see, you can have a partition between control plane or a leader, or you can have a network partition between leader and a follower. Heartbeat handles the case between control plane and the leader, right? So that's easy to detect. But what happens if there is a network partition between where a follower is cut off from the rest of the cluster? How do we detect that? So to detect that, One another aspect is each follower is also heart beating to the leader, which is also sort of piggybacked with a fetch request where it's just fetching data from the leader. So there are two heartbeats where machines are heart beating to control plane, and then machines are also followers are also heart beating to the leader. So as soon as leader gets to know that some follower is not heart beating to it's dead. Leader again doesn't take decisions on its own. It's going to tell control plane that, hey, I haven't heard from this follower in a while. Perhaps you should remove it from the in-sync replica set because that machine might really be down, and then control plane does the stuff. To recap, we went back to a producer scenario. We talked about there's much more happening at step 3 over here. So I'm going to quickly go through what more was happening in step 3. In step 3, when we were actually sending the record to the leader was persisted in its own disk, and then it is sending the record as part of step 3b to its followers. And then it waits for an acknowledgement for both of them. So once it has acknowledged that both have that record, it is going to increment its high watermark or consider that record as committed, as we talked about earlier, and then tell the producer that, hey, all is good. I got your message over here. Interestingly, over here, there's huge scope of errors, right? Like, what if one of the followers didn't send back an acknowledgement? What if everything was well, I incremented the high watermark, but I wasn't able to send acknowledgement down to the producer? There could be many cases of failures in this distributed setup. And now that's why we need to have some sort of a formal modeling mechanism to reason about it and to ensure that all the concepts that we talked about, ISR, high watermark, leader epoch, replication, interaction between data plane and control plane, network partitions, there's too many states to keep in your head. If magically I had a system where I could model these scenarios, and using the computing power, I could compute all the permutations that could happen in my system and then verify that my algorithm is correct, wouldn't that be sweet? So that's what we will try to do over here with the formal modeling part over here. So TLA plus, this is the official definition, or it was invented by Leslie Lamport, very popular in the modeling domain. But let's talk about informal definition of TLA plus. So don't read into it. This is how I say what TLA plus is. So TLA plus allows you to define your system states. So it tells you that, hey, I have this system. It can reside in these states. For example, in our case, would be like a broker could be a leader. It could be a follower. These are different states. And then it could define transitions. You can define transition between state. For example, I could say, hey, a follower becomes a leader when control plane tells it to do so. So I can write that using code. Once I write that using code and define these all states and transitions, and then I can run this model through a model checker. What the model checker does is it explores all the different permutations that could happen with respect to two different calls happening concurrently. And at each of these these calls, it is going to verify special invariants or contracts hold true. And if any of the contract is broken, that means you have a bug in your algorithm. So how does TLA plus look like? This is a very small hello world over here. You'll see that we have something called next. That's the init is the initial state. And so initial state can move to different next states, right? So currently we define two different next states over here. We can say init can either go to hello world or init can either go to goodbye world using the next thing over here. And then it can either go here. So when we run this model checker, it will basically check for both of these. One case when hello world goes to hello world, or when hello world goes to goodbye world, both are possible. And then at each of the states, at a snapshot of a state, it's going to check this invariant, that messages that I have defined over here should either be A or B. So that's the example of an invariant. It's a bit abstract. Let's see how it looks like in Kafka. So in Kafka's world, when we talk about different TLA plus states, these are the different set of actions that could happen on a cluster. This is not an exhaustive list because this model that we're working on is still in progress. I'll leave a GitHub link to this model towards the end of this presentation. But let's look at a couple of them, right? So what we are saying is, from a cluster's perspective, when the cluster has initialized, it can, let's say, receive a call to become a leader, or it could receive a write directly, which is a leader write, or it could receive, let's say, a controller could decide to shrink ISR, which is reduce the number of machines in the in-sync replica set. The way how we model a machine failure over here is we say that, we forcefully say that controller will shrink the ISR, because controller sends shrink ISR only when it has detected a heartbeat is not there, right? So what we say is, if a machine is going from state A to state B on controller shrink ISR, then that models a scenario when that machine was actually down. So these are the set of states which we can define to go from initial state. Now, for each of these states, we have to define those states a bit, right? We have to say what happens in each of the state. So let's take an example for one of them. So the first one over here that we'll touch upon is leader archive to remote storage state, which is, there's lots of stuff happening in parallel in our distributed system. But one of that stuff that's happening is my leader is continuously adding data to the remote storage. KEP 405 that I talked about, the feature that's going to come out in 3.6. So we're writing this TLA plus model to verify that the algorithm, the replication protocol changes that we have done to add that new feature doesn't break anything existing, or it doesn't impact the state of the system. So what leader does is, like, asynchronously behind the scenes, leader is archiving to remote storage. And the way how we write the state, we say there exists a leader in all of replicas, where replicas is a stateful object, such that all these conditions hold true. So the triangle you see over here, read it as an AND statement. So there exists a leader in replicas where the first line is true. If the first line is true, only then the next line would execute, because remember, like, these are AND conditions over here. So if the replica presumes leadership, which means that replica itself believes that it's a leader, then if the remote log get end offset, which is the last offset in the remote storage, is less than the get high watermark of the leader. Why this condition is important? Because with this condition, we are saying that you can only move data to remote storage if the data is below high watermark.
So quick time check. We have 5 minutes.
Yes, I'll quickly wrap this up. And then the third thing we are saying is, once that condition is true, then let's append this record to the remote storage. So those are the three things that we did over here in this state. And now we have had the state transition. How do we check the correctness of it? We check it using an invariant, where we are saying that the log consistency should be okay, which means that no matter what state our system is in, for all ISR, which means for all machines in our quorum state.isr, if we look at its offset from the start offset to high watermark -1, my replica log between leader and ISR should be consistent. That means all my machines in my ISR should have a common prefix with the leader. And if you check this every time, no matter what state is happening in your system, this should be true, and this gives us correctness of our code. So lastly, what I would have is, we have a state. This is how you run a Kafka, or this is how you run a TLA plus model. So I'm just quickly going to skip the happy part over here, but I am going to touch upon the part which could be useful, which is I intentionally introduce a bug in the algorithm over here. So what I do is I say here, hey, you know what, when controller is shrinking the ISR or updating the ISR, don't update the leader epoch, don't increase it. Then I go to my model checker and I run the model checker, which is basically going to check across all permutations of that particular state. And when it's running, it's going to fail at a certain point of time after calculating a bunch of states, as we'll quickly see. And once it fails, then we need to understand why it has failed. And the reason for why is something that we would be able to find out from this one. Let me quickly go to this failed part here. So now we know that it has failed. On the right-hand side, you can see what are the different states it has executed, and you can also see what is the sequence of states that occurred which caused it to fail. And this is how you can potentially debug this particular thing. So this is an example on how TLA Plus helps you in getting in understanding that a failure has occurred in your algorithm and a change has actually caused a failure. Can we do more from it? Yes, it could actually serve as a live specification for your replication protocol, because you read the TLA plus spec and you know what's going on. You can automatically generate integration tests for your code, because once you know the contract, you know the states, you generate integration tests to test your implementation. And that's where we ideally want Apache Kafka to go, and we're working towards that in the community. So with that, to a rushed end towards the end, I have, so I'm open for questions at this stage for the limited time that we have.
Yep. Thanks. Thanks for the great presentation, David. So maybe I will read one question, and for the rest, maybe you can answer them offline. So the most upvoted question is from Buman Vias. How to recover specific message from Kafka?
How to recover a specific message from Kafka. So I assume you mean that perhaps, let's say a message was written on the cluster, it was sent to the producer. It will make sure that that message is replicated in the replicas, right? So it would ensure that at least n replicas, or the whatever is your configure number, has that message. And even if n-1 of those replicas, so even if like one of those replicas is alive, when a new machine comes up which doesn't know about that message, it is going to sync up from that machine and treat it as a source of truth. So n-1 goes down, single broker remaining, a new broker comes back up, it is going to ask that broker, hey, tell me all that you know, I'm going to treat you as the source of truth. And it's going to replicate it from that. And once it has replicated, it has recovered all the messages, so both are in sync, then it is ready to say that, hey, this is the produce and consume can begin from now on. I don't know if that answered your question, Bhuman, but or I can answer that on the chat for you as well to have more clarifications.
Right. Yeah, we are right on time. Thanks again for the great presentation, David. So I will leave it to for the introduction of the next talk to Gary.
Yes. Hey, let me introduce the second speaker, Ben Chambers from Cascada. So Ben is a technology innovator with an extensive background in data processing, machine learning, cloud computing, as well as software engineering. So currently Ben is leading the Cascada open source project, which is a modern event processing system. that transforms how event-based data processing is done. Previously, Ben co-founded Cascada, which is a startup specializing in advanced data platform for machine learning applications. Prior to its acquisition by DataStax, Ben played a pivotal role in driving Cascada's technical vision and implementation. Before Cascada, Ben was a software engineering at Google, where he made a lot of contributions to Apache Beam, specifically implementation of windowing and triggers. This is Apache Beam. Actually, we use that in LinkedIn as well. It's a open source data processing framework. Introduced the first unified programming model for both batch and stream processing. All right, welcome, Ben. Passing it to you.
Hey, thanks, Gary, for the great introduction. Everybody can see my screen, right?
Yep.
Yes.
Great. All right. So yeah, as Gary said, I'm going to talk about a lot of the work that we've been doing at Cascada and kind of this idea of timelines and how they help us with temporal queries, which is really particularly relevant to stream processing. So I'm going to talk about some of these kind of challenges that we saw with temporal queries that led us down this path of introducing timelines and building Cascada around them. I'll introduce the abstraction, what we mean by a timeline more specifically. And then we'll look at kind of how timelines help us express these really interesting temporal queries and how Cascada lets us execute those efficiently. I mean, this should be pretty clear to this group, but recently, since the introduction of stream processing, especially and these big distributed streams like Kafka and Apache Pulsar, events have become ubiquitous, right? We can look at system logs, IoT data, we can derive events from other events, we can look at API call logs, we can go to a database and look at the change data from that database. And so events are everywhere. And at the same time, we started to draw tons of insights from those events. Cascada was originally focused a lot on predictive analytics and creating these predictive ML models to try to predict, based on the current feature values, what's going to happen in the future. How likely is this user to churn or something like that? But you can do a lot of things with events. Drive real-time dashboards, do historic analytics, things like that. But depending on the system that you're using, it can be really hard to actually make sense of those events. So, if we consider like just a standard SQL database, all of these events are just rows in a data, in different tables associated with different users happening at different times. It's really hard to see any kind of pattern emerging from those events. But if we take those events and just organize them by the user and by the time at which they happen, we can start to see a lot of interesting patterns emerge. And maybe this first user, Aaron, we see things like after they win, they send a message. Brad, we see, has lost a bunch of times and then stopped playing. Carla, we see, kind of loses a few times, makes a purchase, wins after a little while, and that happens a few times. So if we look at what was useful in kind of spotting these patterns, we see things like the order of events, not just within one kind of event type or one topic, if we're looking at Kafka, but kind of between event types. It's not just the ordering of game over events or losses, it's the sequence of losses and purchases and wins and messages that all matter. We also see that it's not just the occurrence of events that's helpful, it's the absence of events, time where somebody hasn't done anything. And as I kind of hinted at, working with multiple types of events is essential. So recognizing after a win what happens. And so if we look at all of these, we like to describe this as kind of the temporal context. What else was happening at that time? It's not just about one event at a time or an aggregation of one kind of event. And that's kind of what led us towards this introduction of timelines. So kind of jumping to kind of what we mean, it's really just what we saw. If I asked you to draw a timeline and said, hey, here's a bunch of purchases made by Ben and Davor, you know, on November 15th, Davor purchased $2 worth of something, right? You'd probably draw some kind of scatter plot like this, showing you what's happening over time. And similarly, I can take those events, those discrete things that happen at specific points in time, and I can aggregate them. I can say, what is the sum of purchases made by each user? And when I do that, I kind of get this natural timeline or the sequence of how did this value change over time? So it was some value, you know, it became a value and it continued until the next purchase and then it increased. And so at the core, this is really just what we mean with timelines, is this kind of visual intuition for how we think about values and how those values change over time. And what's particularly helpful about that is that we can use timelines at every point in our temporal query. We can take input from a stream or from a database that kind of knows which facts are true for periods of time, and we can convert those into discrete timelines and continuous timelines. And we can write our query kind of combining those timelines in useful ways to make new timelines, and then we can output that timeline. And in this model, the input can come from a database, from a stream, from you know, kind of Parquet files in an object store. And the output can be produced as Parquet or to a stream. So we really get to kind of choose how we, you know, interact with the system independently of how we structure our queries. And one of the really useful things about that is if we look at this timeline, there's actually multiple questions or multiple ways of outputting it that can be useful. So if you think about this original use case of predictive ML, training a model, we might want a bunch of training examples from every point in time that timeline changed. So every interesting point. And if we just take all of those interesting points, that gives us a history or a sequence of all of the changes. We can visualize it. We can train an ML model on that history. But another useful way of looking at it is to say, just what is the current value for each user? What is the value for each user at a point in time? And so we can just take that same timeline, that same query that produced it, and observe it at a specific point in time, or, you know, materialize its latest value. And that way of observing it is independent from how we write it. So far what we've seen is that, hey, timelines are this pretty natural visual abstraction for temporal values and kind of manipulating values over time. But you know, as I suggested in the agenda, they're not really useful if we can't write interesting queries. So this next section, we're going to look at a few queries with timelines. I'm using an e-commerce kind of made up example, continuing down these purchases. And kind of the simplest one, I'm not going to spend a ton of time on it, is this one that we already saw. I have a bunch of purchase events or purchase amounts, and I can aggregate that to make a timeline showing how that the total amount purchased changed for each user over time. And I can do that, you know, with basically, you know, Python functions or kind of SQL like aggregation, where I say take my purchase amounts and sum them up. Or I can use a more kind of Pythonic or pipe syntax. You might have seen, I think Apache Beam Python SDK has something similar. I don't know if it's pipe or two arrows, but you know, it's pretty intuitive sometimes. And we generally find that this way of writing things tends to be helpful for really long queries where we can express kind of a sequence of logical steps for kind of the temporal query we're building up. But where it starts to get more interesting is when we start to talk about like things like windowed aggregation. So how much has each user spent this month? And again, it's really easy to picture what we might want. You know, we take these events and then at December 1st, the start of a month, the current sums drop off. Nothing has been spent by anyone so far this month. And then as purchases gets made, we see the aggregates start to kick in. And then January 1st, we see them drop off again and start over. And changing that original query that we wrote is really simple. We just say, hey, we want to take the sum aggregation and we want to do it since the beginning of the month. So that's pretty helpful. But so far, a lot of this is pretty easy with existing systems. I mean, it's what we made Beam and things like that for. But where this starts to get really interesting is when we start to get into things like data-defined windows. So here, we're asking for each user, how many page views have occurred since the last purchase they made? So if we go back to trying to make a machine learning model, we might reason about and say, hey, users who have viewed items more often or a lot since their last purchase may be getting ready to make a purchase. So here, if we look at this visually, we see that we have two timelines kind of that factor in. So when Davor views a page, the count of page views goes up. When he makes a purchase, it drops back down to 0. This is logically what we're thinking about. And we see that this query, again, is really simple to write with windowing and kind of this rich temporal functionality. We just say, hey, I want to take the page views and I want to count them in a window since purchases have been made. And because timelines are inherently grouped by entity and inherently ordered by time, I don't have to do anything to join these two streams or join these two tables and order them by time. I can just work with all of my events in one place while I'm writing these queries. As kind of an aside, we played with writing similar things in SQL. Now, I will say I don't believe that this is Beam SQL. I think this is like a standard SQL, PostgreSQL, stuff like that. But we start to see some of the things that are hard to do in this system. And I believe that these would be hard to do in streaming SQL as well. I have two tables or two streams that I want to work with. I need to union them to create one logical thing so that I can say, has a purchase happened yet? And doing that in SQL, I also need to make sure that each of those streams have the same schema or the same set of columns. So I end up playing games like putting a 1 in there if it was a page view or a 0 if it's a purchase so that I can work with that later. And then I end up saying, well, if I want to reset my count every time a purchase is made, what I really want to do is actually have a sum that is grouped by the number of purchases I've made so far. But that means that I have to kind of compute in 2 steps. So first I compute my purchase counts partitioned by user, and then I sum up my page views partitioned by user and purchase count so far. And so all of these tricks are part of kind of just make it hard to work with these temporal queries in SQL. So going back to kind of timelines in Cascada, one of the last really useful features that we found is kind of temporal join. Other systems also call this as-of join. So the idea here is, what is the average product review at the time of purchase? And here, we might find that some users prefer purchasing items that have higher ratings. And the issue here is we can't just compute the ratings for an item and then join with that, because the ratings may have changed. If I bought an item 3 years ago, it's likely rated differently than it is today. And so what we want to do here is say, well, look, Ben made a purchase of a gear at this point in time. What is the average review score for that kind of item at that time? And here we kind of see where it's helpful to start chaining some of these operations together, because we can say, start with the review scores and key them or group them by item and kind of compute the average. So now you have that first timeline on the top, this average review scores by item. And then take your purchase items and look up that item in that data that we've just made, that average review scores. And so that gives us this temporal join. And again, if we look at SQL, it's painful. I'm not going to try to explain this to you guys. It's lots of steps. It's doing things to work with both purchases and reviews, doing things to work across different kinds of grouping, because we're grouped by items sometimes and grouped by users in other places, and things like that. And if we start to look at bigger and bigger examples, we see this repeat. So this was a churn notebook we took from like some Spark SQL examples I think the Databricks put out. And it's like 63 pages of Spark SQL. And it's doing a lot of really low level manipulation, things like we just saw, all these different tricks for working with time, different kinds of events. And when we converted that to use timelines in the Cascada engine, it turned into 2 pages and basically computed the same features. And so the big takeaway here is that, you know, if every time you have something temporal question that you want to answer, you have to go find all of these little tricks to express it in SQL, you're just going to stop asking that question and ask something else. And that's really a problem. I mean, if that's the right answer, if that's the best feature for training your model or the best set of features for making a model, you need to be able to express those. And so using timelines instead of kind of SQL's unordered relation is a really helpful way of reasoning about events and temporal data. But again, you know, it's great we have this new abstraction, this new way of visualizing information. It's great that we have this new way of writing temporal queries, but we also need to execute those. So we built the Cascada engine to execute them. And I think this is an interesting place to start when we talk about executing these kinds of queries efficiently. Is what we see is like when we compare Cascada to DuckDB, which is a pretty nice, pretty efficient, operating on Parquet data, running SQL on a local machine pretty quickly. We see that, look, on simple things, basic aggregation, Cascada, DuckDB, they're both pretty quick, under a second or two. And on some things, DuckDB and traditional SQL does actually win. Like the windowing with history. But when we get into these more complicated temporal questions, we start to see that DuckDB's time gets significantly higher. And this was using DuckDB's as of join to do, temporal join here and things like that. And so we see that, like, just by specializing for this use case of timelines, we're able to execute this kind of query much more efficiently. And so what do we mean, or what are some of those things that make that more efficient? So one of them is kind of taking advantage of columnar compute. So, Parquet files is a nice columnar storage format. Apache Arrow provides really good, really fast columnar computations that are much more memory efficient than operating row by row. At the second layer, doing a lot of things to specialize for timelines. I said that they're partitioned by entity. I said that they're ordered by time. Taking advantage of that throughout the system leads to a lot of gains. And found at the highest level, making the system incremental, so you can run it over your entire data set, or you can say, I ran it yesterday, just run it over the stuff that's changed, or load up some state in memory and run on rows as they arrive from the stream. And you can kind of choose to trade off, how big of batches you operate on to reduce the cost by doing more in a columnar fashion versus, how much freshness you want. And so when we start to look at the tricks, the first big one is to take advantage of order. And there's this really interesting temporal property that we see in all of the queries. And that's that, look, you're never going to use a value from the future. It hasn't happened yet. And in fact, in like an ML world, this might actually be a really big problem if you could use a value from the future, because it leads to leakage and kind of corrupts the model that you're making. And when you look in the past, it tends to be the things closest to now that actually matter. And in fact, we can generalize and say the only thing that matters is that the events that happen now, because I can aggregate into state and have all of the past events summarized in my current aggregation state. And so I only care about the current state and the current events, and that gives me the next thing. So I can just operate in order. And that assumption lets us do a lot of really powerful things. Say that we have to go read 4 files that are kind of spread out over time. Instead of having to have all 4 files open and combine them and do my query, I can just read 1 file at a time. And if I'm at a given point in time in my query, I just need to have the file containing that data open. If I'm doing a windowed aggregation in a system like SQL, I might have to keep all of the windows open. Or if I'm in a streaming world with, late data and things like that, I might have to keep some neighborhood of them open. But if I have a single point in time that I know I'm at, I only need to keep that window open. And so instead of having to keep a bunch of partial aggregates and maps and indirections to get to those, I just have to store the current one for each entity. And similarly, when we look at like as of join, instead of having to store all of these past values, and then when I need to do a lookup using the value that has occurred with a maximum timestamp less than now, and kind of doing these complicated searches, I just have the current value that I'm looking up. And when I do a lookup at a later time, I can just pull in that one current value. So now I've gone from searching through time for the right value as of now to just doing a direct index lookup. Of course, we all know that providing order might be hard, right? Big sort is a big benchmark for a lot of big data systems, and it's hard. But the interesting thing is that a lot of systems nowadays make it so that providing order, especially order by time, is actually much easier than doing an actual sort. If we look at event streams, events arrive mostly in order, especially within a partition. If we look at data lakes like Iceberg and Delta Lake, they tend to partition data by day. And if I take each file, which represents a single day, and sort it, and then I consider those files in order, I've now sorted my whole data set without having to do anything like big sort. And then the next part here is that every query tends to operate on the same set of inputs, and we can sort them once before we run any queries and just read them in order many times. This is really useful for kind of interactive exploration, developing your queries, working within a notebook, doing data science. And then the rest of a query is, a lot of standard SQL operations, things like unioning multiple files or streams together, applying projection, joining, doing output. But every single one of these can take advantage of order in interesting ways. We can do a merge join instead of a hash join and things like that. And so I'm not going to spend a ton of time here. The idea here, is like, hey, we want to be able to take advantage of multiple threads. We want to be able to take advantage of multiple machines. That's great if things are embarrassingly parallel. But I've just said that we want to do things in order. And that kind of synchronization potentially violates that parallelism. And the trick here is just like with SQL, you can go and make a plan and you can divide your temporal query up into parts where each part can kind of operate in parallel and run as fast as it can. And it just communicates with the next part by sending some data, shuffling it to the right places. And your synchronization is really just that shuffle, lining up the data, merging it, and sending out these ordered streams. And then at this highest level, I kind of mentioned incremental and checkpointing. And so what's cool about this is, my animations got screwed up. This is supposed to show this, processing from input one. And then when new input arrives, you don't want to go and process input one and input two to produce the output over the entire stream so far. Instead, you want to just write a checkpoint after input one, and then you can load from it. And so that lets you kind of do this incremental thing where you only process new data. You don't have to process all of the data. But because the system is really efficient and can handle that, when you develop a new query, you can just run it over your entire history and kind of backfill or fill things in. And then you can start running incrementally your streaming. The other thing that this shows, and I'll mention it here because I'm not sure if my next slide is going to be screwed up too, is this also gives us a really nice way. I'll just check the next slide. Yeah, so I'll talk about streaming briefly. So when we're in this streaming world, as data arrives, I can just keep that state in memory. So instead of writing it to a checkpoint, loading it from a checkpoint, and kind of doing incremental batch, I can just say, okay, after input one, here's the outputs. I still have all my accumulators or my aggregates in memory. Input 2 happens, I can update that and output things and kind of keep going. And then the slide that's missing is supposed to talk about here. What do we do about late data, right? This is something that a lot of streaming systems like to talk about. And the interesting thing is that if we have multiple checkpoints, so not just the most recent, what this is showing is like, look, input 3 arrived and it had some late data that includes the same times as input 2. So this isn't strictly ordered. We can just say, okay, well, instead of starting from checkpoint 2 and replaying just input 3, we can start from an earlier checkpoint and reprocess inputs 2 and 3 and produce the final answers. And this is really nice. It's kind of like this optimistic late data handling. You know, continue processing and outputting as quickly as you can, handling your late or handling data as if nothing will ever be late. If it does happen that you encounter late data, you just rewind to an earlier checkpoint and you can process everything forward from that in the right order. You can also use this, you know, if you realize you made a mistake 3 days ago, you can just fix the data, rerun incremental. It'll say, okay, well, I had some new data from 3 days ago. Let me go back to a checkpoint from there and play it forward. And so kind of really using checkpoints and multiple checkpoints gives us this nice kind of optimistic late data handling where as a user, you just don't have to worry about it, right? You just make these checkpoints and it'll kind of minimize how much computation it needs to do to adapt to the changes in data that you've made. And so kind of wrapping this up, you know, Cascada is this open source implementation of timelines, gives you this timeline-based temporal query system and this execution engine that's efficient enough to run on just your machine and process tens of millions of events per second. It gives you these type check queries that have really useful errors, this high performance engine, and this end-to-end incremental batch and streaming, and this ability to kind of run on history and then switch to a stream as you need. And so kind of finally, if this is interesting to you, we're doing these kind of hands-on workshops where you get a chance to play with Cascada on your data and talk to one of us from the team. And you can sign up for that at this workshop link. You can just go to Cascada.io to try it out yourself, or you can come join us on the Slack community at Cascada.io/community. If kind of temporal queries in this problem domain is relevant or interesting to you, we'd love to talk to you and understand your needs and see if we could help you meet them.
All right, thank you. Thank you, Ben. We have a few questions in the Q&A session. Let me just read it out. The first one, with regard to reading input files at a certain time point, is that file a snapshot of all the items at that time point?
The most common use case that we think about these input files for is things like data lakes, where you can imagine you know, one file per day. So it's not a specific set of times, it's like a whole range of times. Or, you know, I think Iceberg and Delta Lake, you can also do like per partition per day or per hour. So, you know, you might say, I have 5 partitions, I'm writing 5 files per day. And so each of those is a full day of data, but it's kind of divided up into 5 based on the producer of the data. So it's not quite at a specific point in time, but it, you know, you could imagine that you're like appending to these files or something like that.
Okay. Just add on to that, you expect the content in the file to be sorted by time?
Ideally, it leads to faster reads. If it's not, we will sort kind of within each file as we read it. And then there's also a system where we can cache that sorting effort. So if you run a bunch of queries on the same file, we say, look, I already sorted it. I'm just going to use that sorted data.
Cool. So you have some sorting capability. Awesome. Next question is from how can one make SQL-like queries against this temporal data?
So I'm not sure what we mean by SQL-like queries. I mean, in some senses, these aggregations are kind of SQL or cumulative SQL queries. In terms of actually writing the queries with SQL, that's not currently something that we support.
Okay. Yeah,
but yeah, it's an interesting question.
Probably the question. do you have a SQL dialect for Cascada, I guess?
Yep. Not currently.
Okay. Okay, cool. One more question from Raj. How is each checkpointed block of data physically stored? Do you rely on log structure, merge trees? If so, does each block contain metadata indicating the earliest or latest timestamps from the records in the block?
So it's a really interesting question, and it hints at upcoming improvements that we intend to make. So currently we checkpoint to a RocksDB, but we've actually started thinking about either log structured merge trees or something like that, where we have these earliest, latest times in one place, and maybe we even have which entities are there. Because one of the things that we've talked about with late data is the need to rewind to an earlier state. But there's an interesting world where we could say, hey, I got a late data for a user and they didn't have any activity in the previous block. So I don't need to rewind that block because my current in-memory value is the same as what I would get if I rewound. And so there's worlds where having just, the earliest latest tells us how many blocks we need to go earlier. But if we also knew like which entities were affected by each block, we can actually start to do really nice things. When we encounter late data, we can kind of roll back just the entities that we need to based on the late data that we received and then play just those entities forward. So currently we just write to RocksDB, but this is definitely kind of on our mind.
Okay. Cool. All right, one more question from Singh. Is the underlying data store similar to a time series DB?
Yeah, and so I think that's an interesting one. And I think there's definitely a lot of similarities to time series DBs, and I think you can do some similar things with them and with Cascada. The big difference that we tend to see is that a time series database is optimized for things like sensor readings or metrics, where you might have one metric, which is a stream of primitive values. And so, one kind of name mapped to the stream, and often it's at a relatively regular interval, like every 15 minutes. Was kind of Cascada's model is more about kind of time-stamped events or kind of structured data at each point in time. You can imagine JSON or Avro being published by Kafka, where you have 30 fields associated with a click event, right? And so there's definitely similarities, but Cascada's kind of temporal queries tend to be optimized for these like structured events rather than these like more simple time series observations, but there's definitely a lot of overlap.
Okay, I think this wraps up this talk very nicely. Thank you very much, Ben. I will pass it on to DJ to kick off the next talk.
Thank you.
Thank you. Thanks, Gary. Thanks, Ben. So it's my pleasure to introduce our next speaker. Mingjun Wu is founder of Rising Wave. Previously, he's been a software engineer working on Redshift at AWS, and also we've been a researcher in the database group at IBM Almaden Research Center. He's got a PhD from NUS in Singapore, and he's been a visiting PhD at CMU. He's been working with stream processing and databases for over a decade. Mingjun, take it away.
Okay, thanks for having me here. Yeah, today I will be talking about decoupling the computing and storage for stream processing systems. Well, yeah, and as just mentioned, I'm currently a founder of Rising Wave Labs, and we're currently working on the stream processing system. We're building a new stream processing system called Rising Wave. And prior to this company, I was at AWS Redshift, the data warehouse, the AWS data warehouse. And my main job was about the vectorization, decoupled computing and storage, metrized views, and some others. And I also spent a couple of years in IBM Research Hub and doing research about database systems. As mentioned, where I obtained my PhD from National University of Singapore and was a PhD at CMU. All right, so before I start this, I just want to do a pretty quick intro about what Rising Wave is, because after this slide, we'll not talk about Rising Wave or some other system. I will just focus on the technology itself. Okay, so Rising Wave is a distributed SQL streaming database. Well, it's so you can think of like, okay, it provides a database system that can provide a SQL stream processing and with Postgres experience, because it's purely Postgres compatible. So as long as you have a system that can connect to Postgres, you can connect it to RisingWave. And well, it's not a modern alternative to Flink. Well, it's not just dropping a replacement to Flink. It's not, because for RisingWave, it's a streaming database. Well, Flink is a unified batch and streaming computation engine, right? Computation framework, right? And RisingWave is an open source project, and it was open sourced in April 2022, and we got a 4.8 GitHub stars, 400 forks, and 1,000 Slack committee members. And RisingWave has already been deployed in dozens of companies, and we have actually hundreds of daily downloads. Kubernetes deployment, actually. And well, if you want to know deeper about what RisingWave is and how to compare with Flink, because I believe that's where everyone here knows what Flink is, right? So here's one page summary. So for RisingWave and Flink, well, both of them can do streaming ETL and streaming analytics. But for Flink, what it provides is a low-level abstraction. And on top of a low-level abstraction, it provides a SQL and Python. But for RisingWave, it doesn't really have the low-level abstraction. It only have SQL interface and Postgres SQL interface. So essentially, you can just use RisingWave like a Postgres, right? But it also have the Python UDF and Java UDF, same as Postgres. Well, so in a database system, how you can present stream processing? Well, essentially you use materialized views, right? And the different part between the stream processing and stream processing in a database system versus stream processing in a stream processing engine is that, okay, you actually can query the materialized views. Essentially, you do not need to dump the data into some other system like Redis, like Cassandra, like whatever else, right? You can just query the systems directly in the query the result directly in the database. And the materialized view, well, I mean, you can build materialized view on top of materialized views, right? So, but for Flink or some other big data systems, it's not like that, because job is a job, and job is more, you cannot create cascading jobs. Probably in some systems you can, but in most of the systems you cannot create cascading jobs, right? And in terms of the internal architecture, which I will focus on in this talk, RisingWave is actually optimized for cost efficiency, while for Flink, where it's actually more optimized for performance. And RisingWave is featured in faster, can achieve fast failure recovery and fast elastic scaling. Well, and can be much faster than Flink. So yeah, in terms of materialized view, you can think of it like this, where you can essentially create materialized views, create two materialized views on top of the one single materialized view, right? So that's a summary about what RisingWave is and how it compares to Flink. But let's talk about more about the technical stuff. And well, okay, so I should actually skip this slide in this talk. Well, streaming data is everywhere, right? And let's think about, okay, you're using operational database, you are using Postgres, you're using MySQL, you are using any database or operational databases, right? In this operational databases, where you have the capture data change, capture data change, right? Or CDC, right? And essentially CDC is a type of streaming data, right? And in the messaging queues, well, you can also use the messaging queues, right? For example, you can use the messaging queues to store the, let's say, Kafka, like Pulsar, Rapanda, to store the to store the IoT data, or probably to store the ad-click stream data, right? All this data are streaming data. Now the problem here is that, okay, now you have the streaming data, but we want to get a real-time insights, right? How can we get a real-time insights? Well, you need to use a stream processing system like RisingWave, Flink, KZDB, whatever, right? And in a stream processing system, what a stream processing system do? Well, a stream processing system does is that it will continuously consume data from upstream systems like your operational databases, right, through CDC, or probably from a messaging queue, or probably from microservices, right, and do computation, and ultimately you can decide whether to deliver results into downstreaming systems like a data lake, or like a file system, or like a optional, or like back to a messaging queue, right? You can decide, okay, whether you want to deliver data back to a messaging queue. So in a stream processing system, typically we probably want to process a stateful operations like joins and aggregations. Well, these kind of stateful operations are pretty common. Just to think about where you want to do, let's say, add monitoring, right? You probably really want to join add impressions and add clicks, right? In the server anomaly detection, you really want to join the TCP performance metrics and the device monitoring metrics. And recommendation system, you really want to join the ethics and the user preferences, right? Well, I mean, streaming joins and aggregations, where these kind of applications are pretty, this kind of use cases, this kind of operations are pretty powerful. But the problem here that we'll be managing, or supporting this kind of stateful computations can also be quite challenging. Why? Well, not just because implementing the operators can be challenging. It's not like that. It's more about, okay, the computation logic can be complicated, right? Probably you want to join not just 2 streams. You probably really want to join 10 streams, right? And the other issue here that, okay, for streaming data, the streaming workload can actually fluctuate, which means that, okay, in a morning time, you probably can suffer from high traffic, pretty heavy traffic, right? But at midnight, probably you do need to handle a lot of data. So the streaming workload can fluctuate. And the main problem here we've spotted is that most of the stream processing system built in the big data era cannot support stateful computation efficiently. Please pay attention that I'm not saying that, okay, this system cannot support stateful computations. I'm saying that this system cannot support stateful computations efficiently. Why? I mean, just think about, okay, if you just want to use one machine to do, let's say, 10 rejoins, then what will happen? Either the operation processing can be stateful computation processing can be super slow, or the system will directly crash, probably just because of the auto memory, right? The system can crash. And let's discuss the stateful computation using a pretty concrete example. That is the end monetization example. So let's assume that you want to join 2 streams. One is the impression stream, and the other one is click stream, right? You have these 2 streams, and if there's a new data comes in from the impression stream, then essentially here we want to maintain 2 states. One is the hash table for the impression stream, and the hash table for the click stream. Once we get a new event from the impression stream, we actually need to check, okay, where there's a match in the hash table for the click stream. If there's a match, we deliver the results into downstreaming systems. Basically generate the output, right? And similarly, if a new event comes in from the click stream, we need to check, okay, whether there's a match in the hash table for the impression stream. If there's a match, we deliver the result, right? So the problem here is that how we can manage the internal states. Well, definitely you can use local storage, right? Definitely you can do that. But the problem here is that, as I just mentioned, in the stream processing applications, the workload can fluctuate. Let's say that's where in the morning time, you probably can suffer from a workload burst. Then essentially, that will mean that you will have you will need to maintain a larger state, right? You need to maintain a larger state in your local machine, right? The problem here, the problem here that in a local machine, the state is actually limited. The state size is actually, the storage size is actually limited, right? You probably have a pretty limited memory size, or probably you only have pretty limited disk size. So if we get a lot of traffic into the stream processing system, then potentially the system can crash. And what makes things worse is that let's assume that we want to join multiple data streams. In this case, basically what we will do is that we will probably use binary joins, right? If we want to join this, if we want to do this kind of binary joins, then essentially we need to maintain multiple data states, right? Multiple states for every single join operator. So which means that it will essentially put a lot of pressure on your local machine. Yeah, then let's dive deeper into how existing solutions like MapReduce style systems can solve the problem. So let's say that's let's say how Flink or Spark Streaming or Storm or Samza can solve the problem. I know that's okay nowadays where they have some modern, better architectures, but let's think about how they typically can solve the problem. The way they solve the problem is so basically all these systems are designed using with a so-called compute and storage coupled architecture, which means that the internal state will be bounded with will be attached to a local machine, right? Let's say that now we have 3 machines. We essentially, what we do is essentially we're partitioning the state into 3 pieces and shuffle and shift these 3 pieces into and maintain these 3 pieces into 3 separate machines, right? If the states if the workload fluctuates, then the state in every single machine will increase, right? But if it keeps growing, then the problem here that the system can crash, because right, as I just mentioned, in a single machine, the memory and the disk is actually limited. So how can we solve the problem? Well, we can essentially nicely solve the problem in the cloud era using so-called quite a standard architecture or modern architecture called a compute and decoupled compute and storage architecture, right? In the cloud era, essentially what we can do is that we can actually maintain a state in the remote storage, such as S3, and do all the computation in EC2 in the local machine, like let's say EC2, right? And well, if what will happen if the state grows larger? Well, in this architecture, you don't need to take care of the state, because as we all know, the S3 volume is actually unlimited. You can consider it as unlimited, right? And if the state grows larger, you do not need to take care of anything, right? You do not need to do anything. You can just keep it growing. And what if we run out of the compute resource? Then the simple thing we can do is that we can essentially just add some more machines, right? We can just add more machines to solve the problem. So let's think about how we can use the so-called modern computing, decoupled computing and storage architectures to solve the data stream joins the problem. As I just mentioned, we can just maintain this. In this application, we can just maintain the hash table for the impression stream in the S3 and the hash table for the click stream also in S3. So if the state keeps growing as the data volume grows, then we essentially need to do nothing, because as I just mentioned, the state is taken care of by S3, and we do not S3's volume is actually unlimited, right? But what if the computer resource is limited? Then the simple thing we can do is that we can just add more machines, right? If we find that where there's a burst and can consume more CPUs, then we can simply just add more machines, probably 2 machines or 2 more machines or 3 more machines to take care of the workload fluctuation. Okay. So the different part, so here's a comparison between these 2 states, two design. The compute storage coupled is architecture and the compute storage decoupled architecture, right? So as I just mentioned, well, if we use the compute storage coupled architecture, then the computation state or the internal state is essentially shuffled into different computing nodes, and every single node it will only need to take care of the part of the state, right? And periodically, we need to checkpoint for fault tolerance. To achieve fault tolerance, we need to periodically checkpoint the local state into the remote disk, right, or persistent storage such as S3, right? But if we adopt the so-called decoupled computing and storage architecture, then the thing will be totally changed. The thing we're doing is that we can essentially use the S3 to maintain use the S3 to maintain the state, and the state actually can serve as a checkpoint because where the state is actually multi-versioned, right? We can always find the checkpoint by checking by going back to the previous version, right? Previous consistent version, right? But definitely to accelerate the processing, we need to cache the data in the local machine, in the compute node, right? So let's think about, okay, using these two different architectures, what will happen if a node failed? If a node failed, we need to recover from the essentially recover from the failure, right? We need to reboot a new machine and restore the state, restore the computer back, right? So what we will do if we use the so-called coupled compute and storage architecture? The thing we will do is that we will essentially reboot a new machine, and reload the checkpoint, reload the state from the checkpoint. And after reloading the state, we can resume the computation. But if using the so-called decoupled compute and storage architecture, then the thing will be totally different. The thing is different because, as I just mentioned, the state is actually stored in persistent storage. And we actually can just boot a new machine and ask that machine to directly fetch the data from the remote storage. And essentially, literally, there's no downtime. There's no very little system downtime, right? And what about this? What about the elastic scaling? Let's assume that you really want to scale from one machine to 3 machines, right? If using the so-called coupled compute and storage architecture, then the thing will be that if we want, we need to shuffle, we need to partition the state from a single machine into probably 3 pieces, ship or migrate these 3 pieces into the newly booted machines, right? And then after migration, we switch the data, we switch the streaming workload, streaming traffic from the old machine to these three new machines, right? And then we can resume the computation. But if we're using the decoupled compute and storage architecture, the state migration, we do not need to do any state migration. Why? As I just mentioned, well, the state, we can essentially ask these 3 newly booted machines to load the data from the remote storage, and they can instantly start computation because the state is actually maintained in the remote storage. But what will suffer? But the thing that the second architecture will suffer from is that for the first few queries, or for the first few, once you start these 3 machines, you will probably see a spike, see a latency spike, because loading the data from the remote storage can be quite expensive and can trigger pretty high latency, right? So the benefit. So what's the benefit? Let's summarize it. So the benefit of using the so-called coupled compute and storage architecture is that it can essentially achieve infinite and independent scaling of computing and storage layers, right? And moreover, the failure recovery can be transient, which means that let's assume that if your machine crashes then essentially you can instantly recover your service with very little downtime, right? So that's a benefit of using decoupled compute and storage architecture. Well, after I mentioned the benefits, well, definitely a lot of people will say, oh, I have so many questions, right? Why this kind of architecture seems so good, right? Should I just adopt this architecture without any, and abandon my old systems? Well, not like that. Because what I just told you about is just the benefit of this so-called decoupled computer storage architecture, right? Then let's talk about the limitations. Well, one big limitation we can spot is that essentially we are actually in this architecture, we are actually storing a state in the remote storage. If we store data in the remote storage, let's say S3, then the problem here that is the read and write from and to S3 can incur high latency, right? The S3 latency can be super high, but for stream processing systems are actually optimized for low latency. This is actually contradictory, right? Well, this is actually pretty contradictory because, well, in a stream processing system, we cannot tolerate high latency, right? So if you search for the AWS doc, you will find that, well, the S3 latency can be as high as probably hundreds of milliseconds. And as we just measured, well, in the worst case, it can probably be as high as probably 200 milliseconds or even 300 milliseconds. So a stream processing system cannot tolerate such kind of high latency. Well, I mean, if just one access, then probably that's fine, right? So just one spike, 100 millisecond spike, right? But if we frequently access S3, then it will be a huge problem. Then how we solve the problem? Well, essentially we can use the technology called the tier storage architecture, right? To avoid accessing the remote storage, excessively, we can actually introduce a concept called tier storage. So what it means is that we can essentially treat the EC2's local storage, which can be SSD or SATA SSD, probably, or in modern days where we typically use NVMe SSD, right? We can actually use the local storage, and the EC2's local storage can actually be considered as the cache in the cloud, right? And then we can also leverage the other type of storage called the EBS, right? EBS is the elastic block service, right? And it can be actually considered as a disk in the cloud. And at the bottom, we still have the S3, and the S3 can always be considered as the persistent storage. So what's the trade-off among these three types of storages? What's the trade-off among these three types of devices, right? So for the EC2, it's super fast, but the problem here is that the data will crash. The data will get lost when the machine crashes, right? If you reboot the machine, you will find that all the data stored in EC2 will get lost, even if you store it in NVMe SSD, because in AWS or in other cloud vendors, they will actually erase all the data if the machine crashes or if you terminate this machine, right? And in EBS, the benefit of EBS is that the EBS is fast enough and actually much cheaper and also cheaper enough compared to EC2's local storage. And also, it actually provides some kind of durability, 5 nines durability. And this means that if the system crashes, then no worries, you will have a high chance to fetch the data back from EBS. But you cannot still not consider EBS as the persistent storage because its durability is only 5 nines durability. It's not like EC2, it's not like S3. as we just mentioned, S3 can be considered as the persistent storage. It's super slow. It can incur high latency, probably 100 millisecond latency. But the good thing here that you can always consider it as the persistent storage, which can provide 11 nines of durability, right? So with such kind of tier storage, how can we manage data? Well, we can just store the hot data in EC2 and warm the local EC2's local storage and warm data in EBS and also cool data in S3, right? Then what kind of what type of then how do we manage this data, right, at different layers? Well, I believe that's okay. If you are familiar with the tier storage, then soon you will find that probably we can use the so-called the LSM tree, right? The log structure merge tree, just like what we have in RuxDB, right? So the idea of RuxDB, the idea of log structure merge tree is that okay, we can essentially we can essentially have the upper layers upper level of data stored in a faster device, and paradoxically we can checkpoint we can compact the data from faster devices into slower devices, right? So that's how the LSM tree and RuxDB works. Yeah. But the problem here that okay, using LSM tree is not good enough. Why? Because well, it can suffer from a huge problem that is the compaction. Compaction means that okay, in LSM tree, as I just explained, we need to periodically compact the data from upper layer to a lower level. And doing compaction can consume lots of CPU device. Can consume lots of CPU cycles. How can we solve this problem? Well, essentially, we can use two strategies to solve this problem. One is called remote compaction, and the other one is called group compaction. So what remote compaction means? Remote compaction means that instead of directly using the local machine to do the compaction, we can actually use a remote machine, let's say a remote EC2 instance, to do the compaction. But the trade-off here is that okay, you will probably definitely suffer from some network traffic, because you need to ship the data from one machine to the other machine and do the compaction in the other machine. And the other machine need to ship the compacted data back to your EBS, right, or some other devices, right? That's a thing probably you need to do. And also, you probably do not need to use a remote EC2 instance. You can actually in AWS, you can also use AWS Lambda function, right? You can also implement the remote compaction in a Lambda function, and that's remote compaction. Then let's talk about the other strategy called group compaction. In a stream processing system, typically you probably want to collocate two operations or multiple different operators in one single machine, right? That's kind of standard, right? The problem here is that okay, these operators may trigger compactions in different time, right? In different frequencies or at different time, right? Then how do we optimize this? So the thing we can do is that we can do so-called group compaction. So instead of asking these operators, allowing these operators to do the compaction on their own, we actually can synchronize the compactions operators, and we can essentially group the compactions in one operation or in one action and ask them to do the compaction at once, so that okay, we can minimize the impact to the execution runtime. Right.
Yingjun, sorry to interrupt. I just want to give you a 5-minute time check.
Oh yeah. I will actually I need to have more 5 more time. Yeah. So definitely, well, I mean that's about the tier storage. But if you really want to optimize the stream processing system, there are many other things you want to do. For example, okay, you really want to optimize the internal state structure, because well, for different state structure, you actually have different access patterns. For example, in hash aggregation, essentially you really want to have a structure that is optimized for point access. But in hash drawing, you actually really want to have a structure that is actually optimized for range scan, right? In Rising Wave, we essentially didn't really adopt any existing data keyword store such as RocksDB, because RocksDB is unaware of the operators or access patterns, right? So some others. So here's a summary. Yeah. So here's a summary of the decoupled computer and storage architecture. That is where the remote storage access can incur high latency and causing unpleasant user experience. But we can essentially use the tier storage to solve the problem. Yeah, there's some other things we can do to optimize the system, but we can skip it here. But one interesting experimental evaluation I want to mention here is that the Rising Wave versus Flink performance. So here, I would like to mention that the checkpoint frequency is set to 10 seconds, which can be super low for Flink. And we also use the EBS as a storage. What you can see here that in this experiment, Rising Wave's performance is much better than Flink. Why this can happen? Well, definitely we have already done a lot of optimizations, right? But let's forget about optimizations. Let's just think about these two configurations. Well, what do we find here? That essentially checkpoint frequency is pretty important tuning knob, and checkpoint can actually severely affect Flink performance, but only slightly affect Rising Wave performance. Why this can happen? This is because Flink uses RocksDB as the state store, and frequency checkpointing can actually cause RocksDB to flush and compact, right? And it may even trigger the RocksDB the write store, right? But for Rising Wave, it's different. It adopts a different strategy, because it will continuously flush the new data into the remote storage in batches, right? And the second interesting fact we found is that Flink's performance on EBS is actually not quite satisfactory. Why? Because of Flink uses RocksDB as a backend store, and actually RocksDB is actually highly optimized for local storage, but not EBS. So here's a summary of this talk. Well, the decoupled computer and storage architecture enables the infinite and independent scaling of computing and storage layer. And we can actually use the tier storage to mitigate the high frequency issues caused by remote storage access. And definitely we need to do a lot of fine-tuned design to further reduce the cache miss rate and latency spikes. Yeah, that's all my talk. Thanks.
Thank you. We have some, really appreciate the presentation. I have some questions, which it looks like we have time to ask real quick. First question is, in the Rising Wave style, where states are stored in S3, won't you need to load the states back to memory during computing time? In that case, how does it save memory usage and computing resource?
Yeah. Actually, I just mentioned in the slide, right? So essentially, you need to have a memory cache. Essentially, that's a cache, but that's kind of different from the Flink's design, because well, for Flink, what are being maintained in the local storage is actually the buffer, but in Rising Wave, what is maintained in local storage is a cache. Buffer is different from cache. Yeah.
Sounds good. Thank you. I think the other question is similar as well. I see there's a follow-up to it, which says it's addressed in further slides, but I'll read the question anyway. Probably naive, but what about maintaining the state in an NFS store while using traditional stream processing systems? Apart from reliability for NFS, what benefits does Rising Wave provide on top of that, since data would still
I think that's kind of a similar question, right? Well, yeah, so essentially, yeah, you can definitely store the data in NFS, but definitely you still need to have a local store or the EBS, so-called storage cloud disk, right, to maintain a state, to accelerate the query processing. Otherwise, well, you will suffer from huge latency. Yeah.
Excellent. Thank you.
Yeah.
All right. Well, that's our questions. We're right at just a little bit after 7:50. So thank you for the presentation, Yingzhen, and thanks to all our presenters. I was going to try to share this slide deck here.
Okay, I need to stop sharing.
Yeah,
Okay.
thank you. Let's see here. Share. No, not that. Oh, bear with me a second. Well, maybe I won't share it. I guess I'll actually, Effie, can I trouble you to share that final slide while I talk this? Excellent.
Yes.
So
Yeah.
maybe while Effie does that, one question I think was covered at the
Sure.
beginning, but I'll ask it again, or I'll mention it again because it comes up. The recording of the talks will be available on our LinkedIn Engineering YouTube channel in a few days. So if you missed it or you want to watch part of it again, it'll be available there. Thanks, Effie, for sharing this. Another common thing that comes up is people ask, if I want to present, how can I go do that? So you can post a message on our Meetup site. You can send a message to FA or Gary or myself, and you could also email any of us if you're interested in presenting. So I think with that, we're all set. Thanks again to all our presenters and to the participants for joining us. Hope to see you again at our next meetup, which will probably be in about 3 months or so. Thanks, everyone.
Thanks. Bye.
Bye.